Okay, hi. This is Katie from my group for Homework 6. This is part 4, and this is when we are going to be coding to solve for the adiabatic flame temperature. So what we're starting out with is this part, and this is just giving us access to the GitHub page that has all the information that we're going to need about the different substances that are in the problem. And then this section is just importing some computational tools. And so .map is where we're going to store variables. And so it just allows us to compute some things in the future. So we're going to start out with P for properties. And we're going to use our CHE, that's what I call it, CHE dot props, and this allows us to have access to the GitHub page, and we want information about methane. We want information about nitrogen, oxygen, carbon dioxide, and water. So this will allow us to get the information about these substances. And so we are going to want to find the heat capacity for each substance, and we're just going to assign those letters so we don't have to keep typing this out. So it's going to be P.CPIGA. B, so it'll be A, B, C, D, E. That's how it will assign it. So we're just going to repeat for all of that. P.CPIGC. D equals P.CPIGD and E. Oops. E. Okay, so that will give us all of the information about each of these substances. And then if we want to see that, and then if we want to see the heat of formation for each of these, we can do that, and it'll show up as an array right here. That's the heat of formation for each of these substances. And so now we are going to want to solve for the heat capacity of each of these. So we're going to make a model. Let's call it heat capacity. And this is dependent on temperature. So we're going to want it to return, let's see, A times T plus B times C over JNP dot, that's the hyperbolic tangent, C divided by T, oops. And then we're going to want to subtract D times E times the hyperbolic tangent of E over T. We want all of that divided by 1,000. So that'll give us a function. And then we want to be able to use this equation. So P dot HF, so the heat of formation plus the heat capacity at 400 degrees Kelvin minus the heat capacity at 298.15 degrees Kelvin. And that should give us these numbers. And then we want to find the enthalpy. And that is dependent on the moles and the temperature. So with this, we want to return JNP dot. So this will give us the dot product of two arrays. And so we want n, comma, we want the P dot Ig, so that's the heat of formation, plus the heat capacity at temperature T. So this will take N and put it through this for each of the values in the array. So once we have that, we're going to make another model. So we're going to just call it model, and it's dependent on C. And so when I'm doing this, I'm going to come down here. C is going to equal dot map, and that will allow us to say that C dot, let's say the amount of CH4 that we have is going to be 1 mole. The amount of O2 that we have, well, excess O2 that we have is 0.2, which is 20%. And then C dot, so the temperature feed, we're going to say is 300 Kelvin. Oops, not bit length. 300 degrees Kelvin. And so if we come back up here, we want to create another dot map. So we're going to use R because that's, I think of results for that. So R dot map. So we're going to do R dot O2. So the ending result of O2 would be equal to the initial amount of CH4 times 2 times 1 plus C dot O2 excess. And then R dot nitrogen, that will be oxygen times the ratio of nitrogen to oxygen in the air, which is 79/21. And then we're going to want R dot CO2, which is just going to be equal to the CH4 that we started out with. And then we want R dot H2O, which is going to be equal to 2 times the initial start of CH4. So that gives us the results of the moles for each of these substances. And so now we're going to talk about the moles coming into the system and the moles coming out. So let's do R dot N for moles underscore in. So that's going to be equal to, we're going to make an array, and it's going to be C dot CH4, so that's coming in. Then we have R dot N2, that's coming in. R dot O2, and then I'm going along this list of the substances that I have, and we're not having any carbon dioxide or water come in, so we're just going to put zeros for both of those. And now we're going to talk about the moles coming out. So that's also going to be an array, and we don't have any CH4 coming out, so we're going to put 0. And then we have R dot N2 coming out. We have C dot CH4 times 2 times C dot O2 excess for the amount of oxygen coming out. We have R dot CO2 coming out, and we have R dot H2O coming out. So now that we know about the moles going in and out, we're going to focus on the enthalpy. So we're going to represent that by H. So R dot H in. We're going to use the function that we made earlier for R dot N in and C dot T feed, because it is dependent on moles and a temperature. And then R dot H out, the enthalpy coming out is going to be equal to that. And then that's going to be equal to the moles going out, and C dot T. And C dot T is the temperature of the flame that we are going to want to be solving. So we're going to finally return, we're going to say R dot H in minus R dot H out. And if we run this, yep, okay. And then we're gonna come down here and we're gonna now define c.t as a range, and this is gonna be kind of a guess. So let's say we're gonna do 1000 for this. Let's say the low, we're gonna have 300, and let's say the high is like 5,000, you know, just a guess. So now if we use this function up here, VSC, we can do VSC equals VSC of C and the model, and then VSC dot solve. That should give us an array. Looks pretty good. And then if we do VSC dot CDF, this should give us our answer. So this is our answer right here. So 2073 degrees Kelvin. And then if we want to make sure that the enthalpy going in and the enthalpy going out are equal, we can do VSC.RDF. And as you can see, the H in and H out are equal. So that means that the enthalpy coming in and the enthalpy coming out are equal. And that means that the total enthalpy would be 0. And that is what we want in an adiabatic system. So that's it for the coding. Thank you for watching. And yeah, thanks.